this morning I typed my name into a web search engine and I got results like pretty similar to the results I've been getting for the last 10 years. The top hit is an NFL linebacker who shares my name. The next hit is a luthier, so a guy who makes high-end guitars. And then there's sort of this long tail of other Keith Adamses who, own a small business and have done some search engine optimization. So it'll be, real estate agents and plumbers and things like that. The odd blog. You might have to go to the second or third page to actually find me. Now, I'm not doing this to sort of pick on Yahoo, right? I actually claim this is a really great solution to the problem of finding documents that match the term Keith Adams, right? If you, knowing nothing else about a human being other than they're interested in websites that have the tokens Keith Adams in them, these are great results, right? These are high quality pages. They're highly relevant to Keith. They're highly relevant to Adams. It's just sort of a different problem. In terms of framing this problem, so I found this fun photograph from the Library of Congress. This is a strike in Union Square from about 100 years ago. In terms of sort of framing this problem, right, information retrieval has this ubiquitous metaphor of like haystacks and needles, right, that you're trying to find needles in this haystack. And if you kind of come to a picture like this and say, I'm looking for people, they're needles, here's the haystack, this kind of leads you to sort of the wrong approach. If this is your haystack and you're looking for needles, some hypothetical hyper-intelligent AI would probably tend to sort of pick out needles from these faces in the front row where you've got a lot of information about the person, or maybe one of the people whose faces is turned out towards the crowd or something. If it was really, really intelligent, it might notice that a lot of them are sort of staring to the right of the frame and figure that there's some human being out there that they're all referring to, and maybe that's the needle you're looking for. But sort of users on Facebook are having this experience, right? Users on Facebook are embedded in this crowd, trying to find one another. And so the purpose of search is to kind of enable that experience, right? Is to make you feel like you're not, sort of lost in this enormous subway station full of 400 million active users, and make it possible to find the people you care about. And that's kind of like my hand-wavy introduction to the sort of broad topic that people call social search. And like all sort of boundaries in computer science, right? The boundary around social search is not perfectly defined, right? There is real overlap with other kinds of search, but the high order bits here that it can be misleading to think about retrieving needles from a haystack. It's more like we're marrying needles in the stack of needles, right? There's not this background of garbage that we're going to pluck out the right thing from. Everything matters. Every user, for instance, on the site is a great result for some other user, right? They have a friend somewhere, or else they're not using Facebook. And I've been using people here a lot because, we have these strong intuitions about social connections and human beings and things that make it easy to talk about those examples. But lots of other objects in social search systems, including the one I'm describing here, kind of have this property. The event we're at right now, the life of a Typeahead query, right? In the grand scheme of things, this is not a globally very interesting event, right? I mean, all of us represent a very meaninglessly tiny slice of the population of users of Facebook. From outside the frame of Facebook, this is not that great an event, but it's a pretty relevant result for all of us, right? We're all planning to be here, and we've told the system that we plan to be here. And sort of one way to kind of model this is just to say that every query has a user kind of riding along with the query, right? Queries are never just sort of, a bag of tokens or, a little tree of Boolean operators on top of bags of tokens or whatever. They're that, but they're also this big set of features that are similar to the documents you're actually retrieving. So of course, Facebook search is not new, right? Facebook's been doing search for several years. And the UI around it has been sort of like a classical web UI experience, right? We've got a text box on the banner at the top of the site. You type queries into it, we take you to a landing page. And hopefully these results aren't totally shocking here. If I type John, I see Johns that I have lots of mutual friends with who, work at Facebook, maybe who are, around my age, a few other little things, right? We've had this thing for a while, and if you take a look at how people were actually using this thing, we found a few properties that seemed exploitable to us. So first of all, to a degree even greater than happens on sort of the published literature suggests about web search engines, these queries are navigational, right? There's really one right answer. You're looking for a specific thing. If you're looking for the person whose name you're typing, you're looking for the event whose title you typed a fragment of, things like that. And in particular with navigational queries, like you don't care so much about, you don't get any partial credit for sort of having other answers that happen to be a little bit like it, right? This is a sense in which that landing page is kind of a distraction, right? People also start these queries out by typing titles, as I observed. And also sort of the ranking for a lot of these queries just wasn't that hard, right? You could predict a lot of our success with an incredibly tiny slice of the bag of features we were trying to use to do ranking here. And so we were trying to get the landing page out of the way. The goal here was to make this Typeahead box where we're providing real results as you type, right? So we're fetching real results with sort of partially specified queries, right, with prefix queries. And we also have this sort of relatively hard deadline here that if you're going to put a bunch of back-end software in between the user typing a key and their web browser responding to it, you better not take all day to do it. So, the search backend I just was showing you, right, the sort of heavyweight landing page search backend has 95th percentile latency around 200 milliseconds. And that's not terrible. You can pipeline that with, doing a page load pretty well. But if you're trying to pipeline that with, a keystroke, that gets a little jumpy and glitchy looking. So that's kind of the introductory material. Before I jump into the sort of anatomy, any questions about sort of what we're trying to do, what Facebook search is all about, what the project we're talking about is, anything? More beer? Okay. Off we go. So sort of the view from low Earth orbit here is not anything totally shocking, right? We've got some user Alice. She's interacting with Facebook through her browser, and her browser's pulling results from a bunch of places. Sort of the most desired of those places is going to be the browser's local cache. Thank you, browser people. We love HTML5. This does make this product better and more tractable. And failing a browser cache hit, it has two sort of remote sources for data that we'll be talking about here in a second. But the richest one there is sort of typeahead.php, which fronts the back end here. And I should probably highlight here. I mean, I'm probably not giving anything away here, admitting I'm a back-end engineer, right? Like I work in sort of the infrastructure side of search a little bit, so I have a particular kind of view of these things. But I'm representing a lot of engineers' work here. A lot of what was interesting and hard about this system was in the UEX area, or in ranking, in ML, in the data pipeline that actually builds the indices for these backends and things like that. So if you have any questions along those lines, feel free to stop me and I'll try and answer. And if it's outside my ken, those other engineers are here and they'll answer. So, it's all fair game. So I said, all the queries include users. So we're going to need a sample user. And Facebook knows a bunch of things about users, right? Whatever information the users filled in on their profile, for instance. But what's interesting for our backend and the sort of features that stood out to us were the user's sort of orientation in Facebook's social graph, right? So you've probably heard the term social graph thrown around. It means something sort of a little bit different to every company. Everybody wants to define whatever edges they happen to have lying around as the social graph. So, when Facebook talks about the social graph, we're talking about sort of two interesting graphs kind of overlaid on each other, right? One is the graph of friendships among people, and on Facebook, friendship is reciprocal, so these edges aren't directed, right? So, Alice has at least 3 friends, one named Bob, one named Chuck. She is also their friends. There are also directed edges to sort of passive objects on the site, right? So Alice is a fan of obscure hip hop, so she likes these music groups Dion Vert and Jurassic 5. Her taste in farm simulation games is as out of kilter as her taste in rap music, and so she plays Farmburg once a day. So there's a directed edge from her to that application. Okay, So let's get moving here. Cache hits are boring, so let's ignore the cache hits. Before you even start typing in the search box, we actually go out and fetch that graph I just showed you. So as soon as you focus, either tab over or click into the search box, we sort of phone home and say, okay, what are these users' first-degree connections from an endpoint named firstdegree.php? And that's going to basically just be, these nodes. The edges are kind of implicit because, you asked for Alice. And what that allows us to do before you start typing is to have something to do when you do start typing. So let's say Alice types the letter B. Right away, we're going to render Bob. We already know about Bob. And we already know Bob's a pretty good result because he's a first-degree friend. Having bought time to go do a real query, we go off in the back end and start, off in the background and start doing so. So, we hit this part sort of, you can more or less imagine. We have an AJAX endpoint in the web tier named Typeahead, and it's a thin wrapper around a thrift service. So we did a practice talk where my colleagues tried to purge the following slides entirely of three-letter acronyms, and we got close, but we weren't able to get all the way in there, and even if we purged the slides, I probably wouldn't be able to censor myself through it all. So just to kind of orient yourself here, if you hear me saying FOF, expand that as friend of friend, right? OOF, or sometimes POF from page of friend, is sort of the, is a second-degree object connection, right? So FOF is hopefully you have some intuition about what a friend of a friend is, right? That's always relative to some other person, right? It doesn't make sense to globally say, I'm a friend of a friend. I'm a friend of a friend of, Jackie's or, Susie's or Tom's, right? Similarly with sort of object of a friend, an object of a friend is something a friend of yours likes, right? You can think of it as sort of a faint recommendation signal. If a friend of mine is into cycling, the odds are slightly higher that I'm into cycling. And occasionally you'll see TA here every once in a while, and that's sort of the whole kit and caboodle out from the user playing with their browser all the way into Facebook's data center and back. Okay, cool. So this diagram here is meant to sort of schematically show how the Typeahead backend operates. It's incomplete in a lot of ways, but probably the most important way here is that you shouldn't, the rounded rectangles on this slide do not correspond one-to-one with boxes in the physical world, right? These rounded rectangles are, services. Each of these comprises some, significant chunk of machines. So your query first comes in through an aggregator, and on the way in, the aggregator doesn't have anything very interesting to do. It just sort of routes queries to these other child services. So this is a little unusual in that we don't have totally orthogonal leaves, right? We don't have leaves that are exactly identical to one another. We've actually sort of specialized these leaves to return different sorts of results and different sorts of features. That has its ups and downs. We think it's worth it. But, it'd be a great thing to press me on in questions. So the aggregator is about to, there's no data dependencies among these backends, by the way. So, it's going to fan Alice, B out to all three of these backends in parallel, but I can't sort of talk in three streams in parallel, so we're going to work through it serially. So let's do friend of friend first. So friend of friend is a distributed graph search service, and it has enough information to recover your second-degree connections, right? And the sort of stereotyped query it answers is, given a user, find that user's friends of friends that match an incompletely specified query, right? So prefix match B, for instance, here. So, we've already seen sort of Alice's connections to Bob and Chuck and ellipsis. But the friend of friend service here has introduced some, knows more about the graph. It can also see another degree out. It can see, Andre, Boris, Bertha, and Terry, and the other ellipsis. And from this set of sort of friends of friends, the people who prefix match the query B are Boris, Bertha, and controversially Bob. So Bob, in addition to being Alice's friend, is her friend of friend, right? There's an arrow connecting Chuck and Bob, I can see a 2-degree path from Alice to Bob. He's a friend of friend. Darn it, we're returning him. Does everybody understand what we're like trying to compute here? Is this, I don't know, this seems like a pretty straightforward thing, right? So, I'm sorry, yeah. Great question. How big are those sets typically was the question. So I'm obviously sort of drawing toy sets here. If we wanted to draw, Alice's first degree graph more realistically, it would be, this is 100 nodes. Actually, a typical user is closer to 120. And then their second degree would be more or less squaring that, plus taking a little bit off the top for overlap. So the overlap varies widely from user to user, and I won't even attempt to summarize it because I actually don't know the distribution. I'm not being coy. But the sort of size of the friend-to-friend set, in normal terms, ranges from something like 10,000 to 1 million. So, some very new users will have, who don't have a lot of friends, will have a tiny friend-to-friend set. For those users, we actually will look 3 degrees out because we want to find good enough results. So we'll call your friends of friends friends for the purposes of heuristic search. Okay. Object of friend here, briefly, very similar, except this time we've got this different graph. It's a little bipartite graph with people on the left and objects on the right. Edges going from people on the left to the objects on the right. In this case, there's some event, Chuck's birthday. Both Bob and Chuck are attending it, so we've got an edge to it. Ellipsis is a fan of Battlestar Galactica, so you've got an edge to it. Chuck's a fan of the Beatles. Hey, they all have a token that starts with B. Disco. Those are our 3 answers. And thanks for segueing me into that. Putting this in slightly more concrete terms, in terms of the implementation challenge here, let me make sure I got the orders, the decimal superscripts right. I think I did. So the contents of the FOF graph is actually all the users on the site, and Facebook is used to disclosing monthly active users to sort of keep ourselves honest. So, we at least have the 400 million monthly active users in there. And there are 77 billion, am I doing that right? 77 billion edges in that graph. The sort of balance of the object of friends graph is a little bit different. It actually has more nodes in it, so it has 1 billion nodes in it. Because it's all of the people plus all the things people create on the site. But it's sparser, right? People like fewer things than the friends they make, by and large. So we have 11 billion edges instead of 77 billion edges. And when we build this whole thing in Hadoop and spit out its index, it's about 500 gigabytes, which is not too scary on disk. But once we're actually ready to run it, it's a lot bigger. And as we'll see, how much bigger sort of depends. Okay, so this is kind of a tricky slide here, so bear with me for a moment. The query we're trying to do here is easy enough to state, right? We're trying to intersect this one big set, which is users whose names begin with B, with this other potentially pretty big set, which is a user's friends of friends. And in a real outlier friend-of-friend set could be something like 10 million users, right? So these are not trivial-sized lists to intersect. And it turns out there's a bunch of reasonable ways to do this. And we've explored a couple of the ways to do this. And I claim that our experience with trying a bunch of different implementations of this boils down to kind of a 3-way trade-off. And the 3-way trade-off itself is actually kind of interesting because at least one of these ways tends to get confused with the other 2 really, really frequently. So a lot of, it's relatively easy to sort of see why there's a trade-off between, compute and memory consumption, right? You can always sort of denormalize things more and take up a little more memory and spend less time computing things. I mean, at the extreme, you could pre-compute all of this, right? At the extreme, you could pre-compute a whole bunch of prefix sets for every user and, spend a ton of disk and a ton of memory on it. So that's not a terribly interesting trade-off. But the cache bandwidth leg is on here because in a lot of ways, that cache bandwidth leg explains a lot more of the real sort of economics and performance of this system than the memory consumption and compute legs do. And it gets confused for both of them. So by cache bandwidth, I mean, a CPU that's starving for cache lines, right? By cache bandwidth, I mean a core that can't make forward progress because the data it's trying to touch, it's trying to rip out of a DIMM somewhere, right? And this is different from compute, right? Compute is something like MD5 sum. Compute is something like that keeps your ALU busy, right? The way you cure cache bandwidth is sometimes by throwing compute at it, right? And it gets confused with compute because they look the same, right? A system, for a lot of user-level profiling tools, a system that's dying for lack of cache bandwidth looks the same as a system that's dying for lack of compute, which is top says my CPU is pegged, right? Top says some process is burning a hole in the CPU. And it's right in both cases, but it's doing it for different reasons, and you have to apply sort of different techniques for them. So I'm going to sort of stake out some implementations that take extreme positions on all of these, right? So we're going to go for the compute corner first. So obviously we're going to need to be able to sort of map a user to their set of outgoing edges, right? So there has to be some map somewhere that gets you from users to a bunch of data, a subset of which has to be the outgoing edges, right? So one option here is what is the data structure that jumps to mind when you start talking about prefix queries, right, which is tries. So for each user, you're going to have this try hanging off of it. The leaves are their friends. The path from root to their friend spells out their name. And you have to do almost no computation to actually find the set of users that prefix match a given query, right? It's very, very easy for your CPU. You don't actually branch much, right? You just sort of the only branches you have to take are decide to which pointer to chase. And if you prefix queried BO, right, you just sort of get one level down from the root here to that BO node, and you know that all of its children are the friends of Chucks whose names start with BO, right? So this is great from a computational perspective. Unfortunately, on sort of 64-bit machines, those pointers are really, really big, right? 8 bytes sort of doesn't sound like that much, but if you think about the number of edges we're dealing with here, and from an information theoretical perspective, right, 8 bytes is enough for a whole edge. 8 bytes is enough information to sort of uniquely determine, right? We said there were 1 billion nodes in OOF, right? 8 bytes is enough to uniquely determine a pair. So every one of these pointers you see in here is an edge that we can't have in our index, is one way to look at this, right? And also the problem is pointers point to random places, right? So this is going to be pointer chasing code, and since there doesn't tend to be a hot set, and this is like an emergent property of this application, you might just have to take this on faith. We pretty much touch the graph randomly. There's not really a partition between hot and cold data and so on. Since pointers point to these random places, you're going to spend all your life sort of missing on the cache trying to cross those pointer boundaries. So something else we tried and actually went into production with this and worked for a long time was a sorted vector of name ID pairs, right? So you can read this as sort of like the linearization of that try. We repeat some information, but if you're clever about compressing the names, then it doesn't have to cost you that much. And the strategy here, now the strategy for executing your query is basically binary search to find the beginning of the names that match this, to find the end of the names that match this, read out the IDs, those are your hits, right? So again, not a lot of compute. And this time it's actually pretty compact in memory. At least we've gotten rid of the pointers. But it's not perfect in terms of memory consumption, right? Because this is still actually going to scale as the number of terms times the number of IDs, right? So all this toy data, I've been doing it with these users who only have one name. Real users have 2.2 names. And real pages have some other distribution of names that has a really big, crazy long tail, right? Pages, people make pages with absurdly long titles for whatever reason. So that's the product we built, and we'd like to be able to search on those absurdly long titles. But it behaves badly with this data structure, and also sort of unlike a lot of information retrieval systems, right? We actually want to keep this graph up to date as it changes. We don't have a crawl step, right? So there's no excuse for being out of date here, right? People don't experience Facebook search as this thing on the side of Facebook that it's okay if it's a little bit out of sync. If they added a group, they want to see the group in search, right? So we actually do have a non-trivial sort of write load here. It's read biased, don't get me wrong, but you can't completely discount the writes here, and you do kind of have an n-squared problem to construct this thing, right? Because if you insert things at random into this, you're going to have to mem move kind of half of it down, right? We're halfway there, folks. So another option that sort of stakes out another extreme in the triangle here is sort of brute force, right? You're going to turn the graph representation into nothing but an adjacency list, right? Every node's going to have nothing but the edges coming out of that node. And you're going to completely share all the information about names, right? So you'll have one big global index that all the names share, labeled the forward index here. And you won't, be duplicating this information that Boris is named, Boris Zhirinovsky everywhere in your index. You're just going to find the friend of friend set, and then by brute force, find out which one of them's prefix match your query, right? So you'd iterate over all of Bob's friends, all of Chuck's friends, stick them all into some container, then iterate over that container and see that everything in the forward index matches what you think. And from an information, in terms of like how much stuff you can cram into the index, this is going to be about as close to optimal as you can do, at least the way I've framed the problem, right? This is all the information we have to remember. But of course, you're recomputing a lot of stuff all the time. You actually lose on both of these dimensions, right? You actually do a bunch of prefix matches, so the CPU is hot. And you're taking a bunch of cache misses because you're going somewhere random in the forward index, and the forward index is too big to fit in cache, and it lives off somewhere random, and so it's hard to read. And so the thing we've got in production right now is like a cute variant on this. This was joint work, by the way. A bunch of us sort of came up with this in a bull session around a whiteboard. But we, more or less have the arrangement I just described, except we've stuck a Bloom filter, the world's tiniest Bloom filter, ahead of every single edge, right? So you have this really crude summary of the prefix of that user's names sort of accompanied with it. And you can kind of do the math about what false positive rate you should expect from using 2 bytes of this. It's not that impressive or anything, but it does quickly reject most of the mismatches. It behaves better in the cache because for any of those ones that you don't have to dodge out to the forward index, you save those forward index things. It behaves better on the CPU because anything that the Bloom filter rejected, you don't have to prefix match. And it also has this kind of nice property that there's a knob we can tune, right? I mean, if titles get longer or these bitmaps get too populated, or any number of other things start happening, right? We decide it's important to do bigrams instead of just the first character, and so on and so forth. We can always just throw more bytes at this and have more or less similar cache behavior. Whoa, that's totally illegible. But that red dot in there is intended to be sort of that filtered force slide I just showed you. And I don't expect you to kind of walk out of this talk and remember all the crazy details of all the crazy ways you can do prefix searching in graphs. I honestly can't without the mnemonic of the slides in front of me. But the thing to get about this is that this is one of those neat problems that doesn't really stay solved, right? As the things we index change, as the query behavior change, as users' behavior sort of drifts over time, as the index gets bigger, as more things get put into it, as the load changes, and the economics change, right? As cache misses become more expensive, as CPU cycles become cheaper, and so on and so forth, we're going to have to keep exploring the interior of this triangle, right? And I'll also say, sort of having come to Facebook, this is my first sort of major project at Facebook, right? And I came here from an enterprise background, and I had a great time in my previous company. I'll talk to you all about it afterwards. Great work, fun company, but we actually did those 4 things, right? I'm not just waving my hands about them. We implemented them and ran them in production-like environments over the last several months. And being able to actually kind of cover that much ground in a configuration space that was this big was really fun. And yes, there are other crazy parts of this configuration space I'm pretending don't exist, right? Like pre-computation. Okay, so let's come up for air here for a second. Yeah. Okay. Sorry. Yeah. This is one of those things I've been sort of camped out in this program's backyard for a while, and this makes perfect sense to me. So, Boris, right? Who the user Boris, who has the name Boris Zhirinovsky, we've set these 2 bits, and those 2 bits correspond to a hash function on B and Z. So if we hit this, if we come through looking for friends of Chuck, whose names begin with B, or forget about B for a second, whose names begin with C. Let's say I'm a friend of Chuck's, I'm Alice, right? And so the backend's already done sort of 1 degree of expansion. It's figured out that Chuck is my friend. Now it wants to find my friends of friend who start with, let's say, D. I'm changing this up a little bit here, but just to illustrate the purpose of the filter, right? So you'd come through here, you'd hash D. We actually just take the lower bits, but whatever. Logically, you hash D. You use that to index into this map. You see it's clear. You know Boris's name doesn't begin with D. Right? If you came through with Z, you'd hash Z, index into this little tiny bit vector here, and see that his name might begin with Z. So you'd have to add him to the set of candidates. And then once you had this sort of set of candidates from that first pass, then you'd go and do the brute force thing in the forward index, right? So then you'd still go through and look up all these candidates in the forward index. But the candidate source is a lot more precise and a lot more dense than if we just took every single friend of friend. You can feel free to count these. No, it's 16. I mean, the right answer here is going to be incredibly data dependent, and it's a knob, right? I mean, I think the one in production for people happens to be 16, but it could change at any moment. Right. The question is, shouldn't you make a bigger Bloom filter for things with more names? Yes, you should. Yeah. Right. So yeah, is there one hash function or is there more than one hash function? Right now there is. The present tense is a little problematic here, right? This is kind of in flight, so I don't know. Do you want to take this one, Jordan? I promised I'd be like handing off to my colleagues in search, so here.
Yeah, so currently in production, I guess there's 2 different cases. In the friend of friend, it's 1 Bloom filter with 1 hash function. And in objects of friend, we actually have 2 different Bloom filters it's like 1 Bloom filter on the first letter and 1 on the digraph of the name. But we're exploring other options. Like Keith said, we probably should change the length of them depending on how many names they have. So.
Yeah, I mean, I hope it doesn't sound like I'm presenting this as like the ultimate solution for all indices ever. I mean, actually, the point of this is that there are a lot of reasonable solutions. Are we ready? Yeah. The question is how we update this, how we live update a structure like this. Is that the question? Yeah, we lock these at the user granularity. So we have these little 1 byte micro locks, and we'd take a 1 byte lock on this part of the map to do whatever we needed to do. Cool. Didn't expect to get live update questions this soon. That's coming later too. Okay, great. So the graph twins return their results, and this really they're the same binary, by the way. You probably realized this the way I was talking about them. This is the same backend running on different machines with a different index that run object of friend and friend of friend. And so the aggregator's got 2 sets of results now, and now there is global to talk about. So I could do a whole crazy deep dive about global, because global is actually the same binary that runs our real search engine, right? That drives the search page. I will spare you that because you guys have been very patient with my graph search spelunking here. But the short version of global is that we've made a special index that removes all the features that are sensitive to the user during the query. Right? So the point of global is that it's going to find those objects that are just sort of super popular to almost everyone. And this might sound sort of not like social search, and you'd be sort of right, right? This is the part of our system that's responsible for returning results and features that aren't that social, right? This is sort of a conventional IR system that's just trying to find relevant documents to your query. We did have to sort of non-trivially modify. I'm kind of lying a little bit saying it's the same thing as Facebook's backend. We did have to do some work for the partially specified query. And also the query cache support was new code too. So, since this thing is, I said that this thing takes 180 milliseconds to do queries, that's still more or less true even with the smaller index. And that's far too slow for Typeahead. However, it has pretty good hit rates in its query cache. So, a lot of the queries that we're getting are extremely short, you can imagine, right? They're, by the time people have typed 3 or 4 characters, you've gone a long way to kind of exploring this space. So there's a pretty good hit rate in the query cache, which is, based in Memcache because Facebook has a lot of experience running Memcache. So I'm going to spare you the crazy deep dive in global and just pretend it hits in Memcache. You do a get on B, and it turns out it's there. Awesome. So I actually did a global query here just to, this is the only real data on these slides, by the way. I've been making up this user and these results and everything else. But this is a real global query that I did for B on Friday. And it turns out the most globally popular objects on the site are the Beatles, Barack Obama, Bob Marley, and Beyonce. And that feels about right. I'm not sure that's wrong. She's number 5. The question was Britney Spears. I just ran out of room on the slide. Okay, so global and Memcache have chipped in. It's time for aggregator to finally swing into action here. The aggregator's real job, right, is actually merging and ranking these results. It's, when we started this out, right, we didn't have a lot of data to train it on, obviously. I mean, we had sort of the click logs from the other search engine, but those are different kinds of queries, and we knew this was going to be sort of only a subset of those queries. And basically, like, we weren't sure sort of what the principled thing to do was, so we built a linear model and we tuned the weights until they felt okay to us, like kind of subjectively. And I'll just cop to that. With the engineering team, kind of would type results, we'd file bugs that turned out to be the result of a weight needing tweaking here or there, and it would happen. We have enough data, so we launched this thing in mid-March. We have enough data at this point to sort of start doing proper training, and we're in the process of doing that right now. So aggregator finally kicks those results back up to the PHP endpoint, and the PHP endpoint sort of gathers enough application-specific data about these objects it's returned so that the Typeahead can actually render the box. Right? So it figures out where these things, profile pictures live, and what type of object they are, how to display them, if it's a page, how many fans it has, all the sort of Chrome that we put in the Typeahead box. And on the client side, we actually finally put these results into a box that you can click on. So the JavaScript on the client side has to sort of blend these results with the kind of prefab results that it got from either the cache or from the first degree endpoint. There's more or less like a static decision made that first degree wins, right? That if you're a first degree result, you're going to stay in this top slot. There are exceptions to that, but it's pretty close to true. And the reasoning behind that being that, like, you don't want to move these things around just because you've gotten more information. If you do, like, the user will kind of come over to the Typeahead box and try to mouse on something, then it runs away from them, and it's a terrible experience. Also, in terms of this UI here, right? I mean, one of the things that you also probably noticed when I put the sort of search engine Typeahead box next to our Typeahead box, is our Typeahead box has a lot more going on visually. That's not just because, like, we don't understand minimalism, right? I mean, the first thing you try, of course, is just displaying the darn titles, and it turns out it's really confusing. You figure if you're typing Jim or something, right? Maybe you're a little fuzzy on, like, what Jim from The Office's last name is, and it would really help to see his profile picture. You're maybe the person whose name you're typing is somebody you just met at a party, and you're a little vague about their last name, and you've only got the first letter of it and whatever. And we also, especially for things that aren't people, we need something to kind of explain why the heck we're showing this to you, right? So, telling you Michael Jackson has, 8 million fans, and that's why we're showing you Michael Jackson, just makes a lot more sense than us just, showing the words Michael Jackson when you typed MI. So we're not quite done yet. So we return these results to Alice, and let's say she clicked on Bob Marley. And the reason she clicked on him was because she wanted to become a fan of Bob Marley, right? So she likes Bob Marley. We are going to synchronously live update our backend in response to that. So that's kind of the first of a couple of interesting design decisions. It's that we synchronously update all of these index structures, right? Information retrieval systems a lot of times have this kind of partitioned index design pattern where you build some crystalline jewel out in Hadoop or MapReduce or whatever, and then you get this bag of noise on the side that slowly accumulates hair until it's time to rebuild the crystalline jewel. So we're taking a different approach, right? We're trying to actually cram all this stuff in memory in a format that we can afford to update. And part of that sort of, part of that is just that users expect sort of synchronous updates and expect that, Facebook doesn't feel like it's some other thing on the side, right? It feels like that box that I type into on the top of the page, it should know about the things I do in the bottom of the page when I make a group or whatever, right, from a user's perspective. And users really, really hate us being laggy historically. Like when we have these periods where this process gets backed up, where sort of the data bus that gets these updates from the application into search gets backed up, we do get more bug reports. Yes, the question is, what do we think about searching newsfeed and our friends' newsfeeds? I think it'd be really cool. We have it on the landing page. It's a vertical there called Stream Search, but it's not in the Typeahead yet. And I've got a punchline about that coming up, don't worry. Excellent question. Okay, cool. Another weird design choice you may have noticed here. This isn't really a document partitioned sort of index, right? A document could actually be in a couple of these different verticals. A page could be both an object of a friend and globally popular, for instance. And in theory, this kind of, is a bad IR thing to do, right? You can get into these situations where something's kind of a mediocre result in object of friend and kind of a mediocre result in global, but if only one address space could see the two of them and put those two rankings together, it would be a great result or whatever. This just doesn't seem to really happen that much, frankly, with our data set. And this might be us just getting lucky. Part of it is that those vertical services are sort of retrieving different features. And you can sort of, if you're going to be a blockbuster in one feature, you're going to either, that's either going to be enough to kind of get you into the top end for that back end, or you're kind of going to be, lackluster in the other feed. It just doesn't happen that often. Like I kind of racked my brain a little bit constructing an example where it would happen. And I don't know if you noticed the Beatles, right? The Beatles snuck in two different places to the results. It came from object of friend, it came from global. But I mean, the Beatles aren't really an example of this going badly. And in return, we get a bunch of flexibility, right? We can sort of push these services separately. We can build their indices separately. They can be worked on by teams that communicate across a very narrow interface. We can turn one off if it's misbehaving and so on. Also, sort of a fun point about this is that real-time search has come to mean search where relevancy is the most important ranking metric, right? So like search.twitter.com or stream searches where you bubble results to the top as they come in and things like that. So we're the old school version of real-time search, right? If you go to Wikipedia and look at real-time computing, they'll tell you that real-time computing is computing where late answers are wrong answers, right? And this is a search engine where late answers are wrong answers, right? There is no result that is so great that we should screw up a user's experience, right? There is no result that is so great that we should, make results jump away from them when they try to mouse through them, or, make the box feel glitchy when you're trying to type, or delay feedback when you're trying to type, right? We have very aggressive timeouts set on the service. And there's a lot to say that I'm not saying here, right? There's kind of the usual big website motherhood and apple pie stuff about hey, query volumes are increasing, the index size is increasing. Those are all true, and those are all very, very challenging. There's the fact that hardware fails. Yes, that does make life hard, and you have to think about it. There's the entire data pipeline, which I haven't talked about here, right? Like a lot of those sort of decisions about how to denormalize things at runtime and how to build things there apply sort of at static index construction time too. So, we built this crazy thing, does it work? So you can sort of see here in about mid-March, we started turning this on. So we didn't go from 0 to 100% in sort of in one fell swoop, lest we melt the site. So we started turning it on, I think, like the 12th or 13th, and slowly ramped it up to about 100%. And this is sort of hits to our heavyweight back-end search landing page. Basically dropped about 30% on sort of day 0. Right. So the question is, how much of this is attributable to the fact that we auto-select the top result? So if you hit return after a Typeahead query, we will actually take you somewhere else. We will not take you to the search landing page. We take you to the top result, which has been highlighted or whatever. So a lot of people accuse us of cheating about that. Like as a keyboard power user, I found that surprising at first. I quickly learned that I have to up arrow to get around the top of the menu to the see more results button. Yeah, and the feedback inside of Facebook is universally that this is somehow sketchy. So what is the figure, 87%? Do you remember, 87? Yeah, Tomo and I are both remembering 87% of users use the mouse anyway. Right, so our impression that people will use the keyboard is warped by our Silicon Valley keyboard goggles. Okay, cool. So the actual figures here, I got a y-axis in here, right? So you actually could, this looks a little bit impressive initially, and then you might say, well, okay, so you guys didn't actually succeed the way you described it, right? We said that like there are all these navigational queries, it's the big fat head, we're going to get rid of it, there's going to be nothing but the long tail left. Like, why didn't this go all the way down to like 90% or 95% or something like that? Well, some of these queries are actually kind of new queries that are happening. The increased volume of Typeahead sort of went up at a much higher slope than the back-end hits went down, right? So nowadays we're doing about 500 million Typeahead queries per day. That is a very generous measure of query, right? That could be as much as 1 per keystroke. In reality, it doesn't work out that way. Like in reality, there's the front end is clever about not sending queries if it already has something in its cache. The front end doesn't send queries if you're still typing really, really fast, right? So I forget, it's 50 milliseconds or something. What's up? Okay. Yeah, it needs to sort of sense that you've paused. So I think it's actually somewhat aggressive. It's like 100 or something. The peak QPS we're putting up here is 33,000. I'm going to go with that. Our 95th percentile latency is really close to a decimal order of magnitude better than the heavyweight backend, so 17 milliseconds. So it's for most users that's going to be dwarfed by the round trip time to Facebook's data center and back, but it's nice to have a lot of budget to spend there. And we have about 1 billion things in the index, as we said. So before I start talking about this, and one of the reasons I didn't want to completely answer your question right away, I need to do a little dance here. Okay, my title does not match the regular expression C.O, right? So I don't announce products, right? I write code for a living. I have absolutely no authority to promise or even think intelligently about future products that Facebook may or may not deliver, build, conceive, discuss, or etc. However, one of the you can still ask the question, well, what's missing, right? What are the things that are in the heavyweight are in the heavyweight search that are in no way surfaced in Typeahead, right? And the big one is user-produced content, right? A huge amount of the value that people get from Facebook is their friends writing them messages, their friends writing wall posts, status updates, comments, the things that people write on groups walls and pages walls and so on and so forth, videos, photos, chat, what the heck. None of those things are in our index currently, and they need to be. This would be a huge technical problem. We'd need to be retrieving a much bigger index. A lot of these cute data structures that basically assume there are a couple of blockbuster tokens that get you all the way from knowing nothing to having the right answer don't work out. And there's some interesting kind of UI problems. If you actually think about like what it would mean to do type-ahead video, I hope it doesn't mean you pop a box into the type-ahead box because that would probably be really lame. And like another interesting direction here is Open Graph nodes. So if you paid attention to F8, right, our recent sort of developers conference, we talked about this new standard Open Graph that basically lets people outside of Facebook build nodes in our graph, right, and lets users construct edges between themselves and those nodes, and actually edges between the objects and other objects for that matter. So we're indexing these things, but kind of like the other things I've been talking about, they're indexed by their title. And that turns out to be an exceptionally poor way to structure the searches for offsite data. For some kinds of open graph node types, right, there are some semantic categories. I'm sorry, I should probably set the context here a little bit. Like, open graph is kind of like semantic web light, right? You don't just give us a node, you tell us what the node is. And it's a much simpler ontology than the semantic web folks have been using. So I mean, it's flat, and there's a type for restaurant, and a type for musician, and a type for movie, and a couple of other things, right? So title queries work okay for some of those object types. They don't work as well for a lot of the other object types. And I'm not going to bother listing the challenges, right? Because there's sort of nothing but challenges, right? I mean, the challenges are all of the challenges of searching a very large document collection with without a lot of information. Okay, so that's what I got. Thank you.